Welcome viewers. In this session, we are going to discuss about deriving the Laplace transform of a function f of t is equals to cos hyperbolic at using the first principle. And by the first principle, the most important thing that you need to understand is about the first principle formula. When it comes to the first principle formula, we know that the Laplace transform of our function f of t is equals to integration with respect to our limits, whereby the lower class limit is equal to 0 and the upper class limit is equals to infinity. We come and have an exponential of negative st. We multiply by a function f of t, and our integration is with respect to dt. So whatever I've written here, this is just the first principle formula. In our next step now, we understand that our function f of t is equals to cos hyperbolic at, to mean that the Laplace transform of now cos hyperbolic at is going to be equals to integration with respect to our limits, the upper class limits starting at infinity up to 0, exponential negative st we multiply by our function f of t was equals to cos hyperbolic at, and our integration is with respect to dt. At this point now, the only thing that we are being required to do is that we change the cos hyperbolic at into an exponential. And by changing cos hyperbolic at into an exponential, we understand that cos hyperbolic x is always equals to a half you multiply by exponential exponential x, you come and add to exponential negative of x, to mean that when we are having cos hyperbolic at is going to be equals to a half, where we are having our term of x, we are going to replace with at, to mean that on this side we are going to have exponential at, we add to exponential negative of at. When we check at this point, we can really say that cos hyperbolic at is equals to whatever we are having on the right hand side. Let us now get back into our working, whereby we say that the Laplace transform of our function f of t is going to be equals to integration with respect to our limits, exponential negative st, we multiply by our function cos hyperbolic at, we agree is equals to whatever we are having here. And we are going to have a half into exponential at, we add to exponential and negative of at, and our whole integration is with respect to dt. Now at this point, we are going to factor out a half because it is not a term of dt, and we open the bracket. By doing that, we are going to have the Laplace transform of our function f of t is going to be equals to a half our integral sign with respect to our limits. We open the bracket, we are going to have exponential negative st, we multiply by exponential at, we come and add to exponential negative st, we multiply by exponential negative at, and our whole integration is with respect to dt. From this point now, we need to simplify whatever we are having at this point. And by simplification of these two products, we are going to use the laws of indices. When we use the laws of indices, it says that when the bases are equal and it is a multiplication, we take one of the bases, hence we add the powers, to mean that we are going to have the Laplace transform of our function f of t is going to be equals to a half integration with respect to our limits. Here, by using the laws of indices, we are going to have exponential into negative s, we add to a, we come and factor out our term of t. This is what we come and multiply out with our term of t. We add to, here also we are going to use the laws of indices. We take one of the bases, exponential, to the powers, we come and add them, we factor out our term of t. We are going to have negative s, we subtract from a, we multiply by t, and our integration still remains with respect to dt. Up to this point now, we can literally do our integration. And we are going to have the Laplace transform of now our function f of t is going to be equals to a half. We multiply by our integration here, we are going to have exponential negative s, we add to a t all over negative s, we add to a. And our integration is with respect to the upper class limit and the lower class limit. We come and add to our integration here, we are going to have exponential negative as we subtract from a t, everything is going to be all over negative as we subtract from a. And our integration is with respect to our limits. Now, let us simplify this bracket by doing away with the class limit. For us to do away with the class limit, now we can come and say the Laplace transform of our function f of t is going to be equals to a half. In this first bracket, we are going to have 1 all over negative s, we add to a. We come and multiply by exponential negative s, we add to a, multiply by our term of t. Our limits we must insert. Here we are going to have negative s, we subtract from a, we come and multiply by exponential negative of s, we subtract from a t, we have there our limits. Let us now do away with the upper class limit and the lower class limit. By doing away with the upper class limit and the lower class limit, we are going to have the Laplace transform of our function f of t is going to be equals to a half into negative s we add to a. We come and multiply by exponential negative s we add to a. We insert the upper class limit where we are having our term of t. We subtract from exponential negative of s we add to a. We insert the lower class limit. The whole of this is for our first bracket here. Let us now get into the other side whereby we are going to add 2. Here we are going to have, let me come and write it somewhere here. Here now we are going to have negative s we subtract from a. We come and multiply by exponential negative s we subtract from a. We insert the upper class limit which is at infinity. We subtract from the lower class limit exponential negative of s we subtract from a. We insert the upper class limit. Up to this point now, we can do away with our class limits. And by doing away with our class limits, we are going to have the Laplace transform of our function f of t is going to be equals to a half into 1 all over negative of s we add to a. We multiply by exponential raised to a power of an infinity we understand is equals to 0. Here we are going to take 0, we multiply by whatever we are having within the bracket. Exponential raised to a power of 0 is equals to 1. We come and add 2. At this point we are going to have 1 all over a negative of s we subtract from a. And we know that exponential raised to a power of an infinity we are going to have 0. And here we are going to have a negative of 1. From this point now, the negatives that we are having at this point and at this point are going to affect our denominators. And we are going to have the Laplace transform of now our function f of t is going to be equals to a half. We multiply by, when we take this negative, we multiply by whatever we are having here on the denominator. We are going to have 1 all over s we subtract from a. Our sign here is going to be a positive. We come and take this negative, we multiply by whatever we are having there, and we are going to have 1 all over s we add to a. Because this one is a negative, this one is a negative. When we multiply by a negative, they are going to be both positives. Let us simplify now these fractions, and by simplification of these fractions, we are going to have the Laplace transform of our function f of t is going to be equals to a half into We take whatever we are having here, we multiply by 1 to mean we are going to do our cross multiplication. And we are going to have 1 into s we add to a. We come and add to whatever we are having here, we multiply by that. And we are going to have 1 into s we subtract from a. We come and multiply the denominators, this one and this one. Here we are going to have s squared, we add to sa, we subtract from sa, this one multiply by this, and we subtract from a squared. Let us now simplify whatever we are having both on the numerator and on the denominator. The Laplace transform of our function f of t is going to be equals to a half into, here now on the numerator we are going to have s we add to a, we add to s we subtract from a. On the denominator we are going to have s squared we subtract from a squared. This one is a positive, here we are having a negative. They are going to cancel out one another, and this is what we are going to have on the denominator. And finally, we can come and say the Laplace transform of our function f of t is going to be equals to a half into, here s we add to s, we are going to have 2s. A is a positive and here a is a negative. They are going to cancel out and we are going to have all over a squared we subtract from a squared. This one and this one will cancel out. Hence, we can come and say the Laplace transform of our function f of t is equals to s all over a squared we subtract from a squared. And this is now the Laplace, deriving the Laplace transform of cos hyperbolic at, to mean that the Laplace transform of cos hyperbolic at is equals to s all over a squared we subtract from a squared. And this is how you go about deriving the Laplace transform of a function cos hyperbolic at. Thank you for your time. Let us meet in our next session, whereby I will be discussing an example of cos hyperbolic using the first principle.